Hello, I'm Yildirim, and this talk is on the paper Digital Fabrication Tools at Work, Probing Professionals' Current Needs and Desired Futures, which was to be presented at CHI 2020. In a nutshell, this talk is about an exploratory study where we investigated the needs and desires of fabrication professionals in micro and small-scale manufacturing settings in order to identify opportunities for digital fabrication tools to support professional users in their work. Digital fabrication tools have transformed the professional practice in small-scale manufacturing. On one hand, these tools are extending the capabilities of users. They leverage machine intelligence and sensing to bring new functionalities. On the other hand, they raise concerns around the felt experience of making things. The computerized workflows automate away craftspeople's agency and control over their work. So the question HCI researchers and tool developers have been asking is, how might fabrication systems become more intelligent while maintaining people's agency over their work? To answer this question, we need to know where the boundaries between machine autonomy and human agency lie. But currently, little is known about what is meaningful for people in making and what is less critical for their sense of agency so that it can be delegated to machines. To explore these questions, we conducted a co-design study with fabrication professionals. We had two goals. First, we wanted to understand the current experience of professionals who use these tools daily. And second, we wanted to know their preferred futures. In what ways do they want tools to support their work? And our overarching goal was to identify opportunities for future tools to understand where and how we can situate machine intelligence in fabrication systems. Before I move on to the details about our study, I want to give you some context about the user group we studied. When we say professionals, we're basically talking about people who are making a living out of using digital fabrication technologies. So our participants involved customer manufacturers that work independently as contractors or business owners, shop stewards that manage shops and maker spaces, fabrication specialists that work on design and fabrication projects in-house, and entrepreneurs who manufacture products as a core part of their businesses. We focused on professional users as they had considerable expertise and agency over their work, yet they were an under-investigated group in prior work, which mostly focused on hobbyists and novices. Overall, they were all small-size, independent workers who use low to medium-end fabrication equipment, and we focused on three commonly used digital fabrication tools: 3D printers, laser cutters, and CNC routers. Most of our participants were fluent in all three of these tools. We had 23 participants in total, and overall they were affiliated with several makerspaces, custom manufacturing shops, university fab labs, and startups in Pittsburgh. We conducted 6 co-design workshops where we had 3 to 4 participants in each session. And in the workshops, we asked people about their current experiences and pain points, as well as their preferred futures. And as I said earlier, we wanted to explore the boundaries between machine autonomy and human agency. So we asked people to imagine a future where they have super intelligent fabrication tools that can do any fabrication task. We asked which parts would they keep to themselves and which parts would they delegate to machines, so that we understand what actions are meaningful and what actions are mundane and repetitive in making. After collecting and transcribing the data from the workshops, we analyzed them using affinity diagramming. Now I will discuss 3 major findings and related design implications from the study. As we were asking people about their current experiences, one thing became clear immediately. Digital fabrication tools in small-scale manufacturing are unreliable and untrustworthy. Every single participant we talked to had a catastrophe story of things catching on fire and machine crashing into itself or into the material. And it's not just about safety. Users simply don't trust these machines to work as they are supposed to. So what happens is they have to monitor them throughout the operation to make sure the tools are not failing. Now imagine a professional tool that asks for its user to sit and watch while it operates because it might fail. This hugely decreases our users' performance and their overall experience of using these tools. So professionals expect their tools to be professional. They don't want machines that require babysitting, which is in fact very disrespectful of their time. This finding reveals an opportunity for digital fabrication tools to perform safer and more reliable. There's a real need for tools with increased machine awareness and sensing to prevent, detect, and recover from failures. More specifically, we need to develop tools that have awareness over themselves, over their performance, and over their workspaces. For example, a performance-aware laser cutter can be programmed to cut through material rather than cutting material at a given speed and power. It can course correct the settings based on results and go back to partially recut the parts it didn't cut through in the first pass. Such tools have the potential to be more resilient to failure. They can sense and recover from errors in their operations, and they can compensate for variations in materials. Our second finding is related to the issue of machine autonomy and human agency. Based on the literature, we expected to find concerns around automation, but counter to the narrative about the loss of agency, we found that professional users are not really concerned about a loss of control and agency. Conversely, they desire more automation in their tools. Here's a quote that pretty much sums it up. From a business standpoint, the less I have to do personally, the more money I make. On my own personal projects, I'd still rather just push a button and have the part come out, because I could be using my brain rather than sitting watching some machine. Now, this was quite surprising. It seemed very counterintuitive at first, but when we looked at where they wanted automation, it started to make sense. Professional users have to repetitively carry out menial tasks such as machine setup, calibration, maintenance, error recovery, and so on. They wanted tools to perform these tasks to free up their time and attention. Most participants were on board with full automation as long as they were able to go back and customize the settings. Additionally, professional users desired new capabilities that take advantage of machine abilities. For example, machines have perfect memories, but when it comes to documenting the work, they're not really helpful. People wanted tools that can document their work, the settings, and the outcomes as an aid in their process. Another example is post-processing. Current fabrication systems offer little support when it comes to finishing, sanding, and assessing the quality. Our participants expressed that it would be super valuable to have such tools that can support their work in these ways. One thing we realized was that the way people described future tools sounded much like an intelligent shop assistant rather than a collaborator. It sets up the machine, registers the material, documents the settings, it knows how this machine is working, it calibrates and monitors the work as it's being done. It makes suggestions when asked, but in a way that can be overridden. This metaphor of a reliable and trustworthy shop assistant reveals a huge opportunity for future fabrication systems that support people's work without threatening their agency. We are planning to address these issues by leveraging machine intelligence, sensing, and actuation to automate menial work and to augment human capabilities in new ways. Lastly, we found that professionals need support in making trade-offs between time, quality, and cost. These people work under constraints such as material costs and tight deadlines, and they need to deliver a certain quality. So they have to make trade-offs based on what the project requires. Sometimes they trade quality for time to be able to ship on time. Sometimes they need to achieve a specific price point, so they prioritize costs, and this is not an easy task. Our participants struggled in making these decisions. This presents an opportunity for future intelligent tools where the tool can support decision-making by negotiating such trade-offs. A better tool would work to understand the constraints of the users, and it would communicate how its capabilities can support the desired outcomes. But how do we measure and negotiate the subjective notion of quality so that a fabrication system can understand the desired level of quality and the quality it can actually produce? That's an open research question that we are planning to explore in our future work. So this was a brief overview of our study. Please refer to our paper for an in-depth discussion, and feel free to reach out if you have comments and questions. Thank you.